Welcome to the Tech Arena Data Insights webinar series. I'm Allison Klein, and today we have a delightful episode for you. We've got Shimon Ben David, CTO of Weka, and Ace Stryker, AI data center lead at Solidigm, with us for an insightful conversation on generative AI. Welcome to the show, guys.
Thank you so much.
Hey, Alison, nice to be here.
So Shimon, this is the first time that you've been on the Tech Arena. Do you want to just start by introducing yourself and a little bit about Weka?
Definitely. So I'm Shimon Ben David. I'm the Chief Technology Officer of Weka. Been with the company for the last 11 years. Yeah, if you can believe it. It's fun to see a company grow from the early days all the way to being a worldwide organization across all continents. Weka is an accelerated data platform for AI and additional accelerated workloads, HPC, enterprise HPC, and we see a lot of it also in media entertainment, life science, and more. It can span between on-prem and cloud, and eventually the value is accelerate time to results. And I think, as we'll see today, some of these the use cases that are considered to be compute bound, we actually see that they're data bound. So by being able to serve the data faster, we're actually able to accelerate the time to outcomes, accelerate training, accelerate inferencing. I think that's the fun topic that we'll discuss today.
That's awesome. Great introduction. Ace, welcome back. You've been on the show before. Do you want to just give the audience a quick introduction?
Sure. Thanks, Allison. Great to be back. My name is Ace Stryker. I work in the strategic planning and marketing group at Solidigm. And so we do a lot of thinking about where the market's headed. It takes a long time to build storage devices, as you might imagine. So our goal is always to be skating to where the puck is going to be, 3 years from now. And so we spend a lot of time and energy these days thinking about AI, thinking about trends in particular in how data moves through an AI cluster or an AI workflow. What are the stages of that work? What are the kind of unique requirements on the storage subsystem associated with those? And so it's a busy new field for us. I heard a great comment in a conference I went to recently where a guy said last week was a very busy year in AI. And we certainly feel that at Solidigm as well. It's changing all the time.
That's the way it feels like at Tech Arena every day, too. It's another opportunity to tell the next chapter of AI delivery. And this is no different. Today, we're going to be unpacking AI inferencing and really how this core capability for generative AI is exploding across the enterprise. Why don't we just start, Shimon, with a definition, a level setting of AI inferencing and how its role has evolved in the rise of generative AI.
Brilliant. So usually I equate AI inferencing into running a program. So eventually, in order to utilize AI, the two main stages is training a model or creating a model that would serve a function, and then running that model in production. So for example, an NLP aspiration, recommender engine, or an LLM that would generate data, image, text, analyze and answer, and then running that in production is actually utilizing it. So that's the simplest way to think about inferencing. Behind the scenes, under the hood, there's so many components in that play: inference servers, GPU servers, even CPU servers, networking, storage, different types of frameworks, continuous fine-tuning, which we'll talk probably more about in this session. The main difference with inferencing in generative AI environments is the bar to inferencing has been lowered. So if in the past I need to have an army of data scientists that would train a model, build a model for my specific organization, train it with my data, understand and tweak it to whatever needs I need to do with it. Now with generative AI, it's fairly simple to just download a model from some model hubs like Hugging Face or others and plug them into my environment and just run them and have them serve what they already know and generate the data that they already are able to generate. And that's already valuable. So for example, chatbots can just easily be created. I know a lot of startups that just started with zero knowledge about AI, but just utilizing inference engines that are remote inference environments, right? So the bar to entry of utilizing AI, of inferencing in AI, has been considerably simplified with generative AI. And by the way, the outcome is also significantly more impressive. We're now able to do and see things that are amazing, starting from analyzing large amount of text, getting some reasoning insights into some interesting thoughts, designing videos, images. It's the imagination is the limit here.
I love that you've focused on the impact, because that's so important to keep into perspective as we go forward with this discussion. And I think enterprises are seeing that. We're expecting a hockey stick of growth in terms of enterprise deployment of generative AI inferencing. Ace, how do you see this shift impacting with demands on infrastructure, especially storage technology?
Yeah, it's a good question. There's a couple of things going on in the inferencing world that I think have significant impacts on the way enterprises are building out their infrastructure. One is simply that generative models are much more data intensive, right? And so the output of those is, as the name suggests, generating new text and increasingly, images and videos. These are all things we're asking these models to do more at the end of the pipeline than we have in the past. And so there are commensurate, requirements, not just on storage, but on the compute as well, to do that in a timely fashion. And we can get into some of the details of that if we really want to get into the nerdy weeds here. But the other thing that's happening more and more, what we're seeing among our customers and their customers, is more and more interest in doing this work at the edge, right? Folks want to move inferencing out of the core data center located somewhere in the world that you're connected to over a network to, in the factory, in the hospital, in the school, right? There's lots of good reasons for that, related to data security, related to, latency and performance requirements, but certainly that's driving a lot of evolving thinking about infrastructure choices as well. It's like, hey, if I'm going to do this in on a single rack in a closet in my local facility here in my office or whatever, I'm going to be thinking about my infrastructure needs in a completely different way than I was, 5 or 10 years ago, when I had to, out of necessity, only do that stuff, from a core data center located somewhere offsite, and perhaps far offsite.
Maybe I'll add to that, by the way.
Go ahead.
So one of the main shifts that we've seen is with traditional AI, the focus was much more around training. And generative AI really enabled inferencing in large scale. And that amounts to, if you look at the data center, definitely plus one on what Ace mentioned about a lot of inferencing going in the edge. But we also see these data centers that were training heavy now explode to be inferencing heavy. So more than 80% of the data center is now doing inferencing, while there are always the LLM companies and the large models, foundational models creators that are still doing the training. Even in an inferencing environment, you'll still do some training, but the amount of infrastructure that's being deployed for inferencing now is massive. And honestly, I think we're just seeing the beginning of it, because as that evolves, as inferencing evolves, training is a fairly understood challenge. And as the amount of inferencing involved with frameworks, with GPU connectivity, with new technologies, we'll see. So
I think that's a really interesting point. And what you speak to is a question of scale. How do you see these infrastructure challenges that Ace has talked about being addressed by organizations when they're thinking about scaling generative AI models across their infrastructure landscape?
So I would say in the past, when as an organization, again, really had the deep knowledge, the MLOps knowledge of creating a model, tweaking it, tuning it to its own needs, it was a very focused use case. And now with modern Gen AI inferencing, not only one model is being used. Even when we're using what we think is a model, usually there's a chain of models that are running behind the scene, outputting and communicating with each other. The scale itself is usually not just for my internal 1 or 2 users or a data scientist running it. It's on its own data set, but even if it's my own internal organization, or I'm actually providing it to my external users, I now need to accommodate for thousands and millions of prompts per second even.
Mhm.
Just the sheer scale or distribution of the environment. Additionally, in previous environments, AI was very experimental. It was very niche. Even if it was running on large scale, it was very experimental. And now it's much more in the core enterprise business. So it has to have all of the enterprise regulations around it: security, stability, resiliency. You need to be able to investigate what a chain of authority for answers, for tokens. So you're now wrapped into this experimental design environments, now move to a complete enterprise resiliency environment. And then the next level is to measure the ROI. In the past, models were run related to the value that they provided. Now in an enterprise environment, there's much more focus around what am I getting compared to what have I gotten had I not used the model.
Now, Ace, Shimon has laid out a really fantastic definition of infrastructure, but I want to get into storage in particular. How do you see storage limitations and data bottlenecks impacting the efficiency specifically of GPU accelerator utilization that's being tapped in AI inferencing?
I think it's important to acknowledge as a storage vendor that nobody that's doing inference wants to, read data directly from disk or write to disk in real time as a first choice, right?
Mhm.
In a perfect world where we could afford petabytes of memory, we would do everything there and maybe just archive stuff on disk at the end, right? But that's not a realistic approach. That's incredibly expensive, and so we have, seen this sort of storage and memory hierarchy evolve, where these tiers work together, right? And so the question is really, what is memory's role in inference, and then where can storage help when you don't have enough memory to do everything that you want to do there, right? I think that's the key opportunity that storage can play on the inferencing side, apart from the archive stuff, which is kind of inevitable and an output at the end of the process. But when you think about these generative models in particular and how they're running, there's a couple of places that storage shows up as a necessary and an important component to keep the GPUs fed. And so one example that I'll mention to you is something called the key value cache. And we don't have to spend a ton of time going into this, but when you're doing inference, the model has to keep track of the context of the conversation, what's already been asked for, what's already been delivered. If you imagine a chat with GPT, right, you may ask it a question and then some follow-up questions, and the model needs to understand that your follow-up questions were based on the initial one. Otherwise, it's going to give useless answers, right? And so when you're talking about these kind of multi-turn interactions with a model, or when you're talking about some of these more recent, really big, sophisticated models, or particularly detailed prompts or inputs going into the model, all those things will blow up the size of this key value cache, this KV cache, to a size that's not manageable in memory all the time. And so that's an example of a place where performance storage becomes really important, because now if you have to offload some of that KV cache in the course of a real-time interaction with a model to storage, then that storage had better be able to keep up, right? And not slow down the interactions or the insights that you're looking for at the end of the process. Another one I'll mention is a lot of these generative AI deployments these days use a technology called RAG, Retrieval Augmented Generation. And, very brief description, you train a model and you get at the end of that training process, based on the data set that you use to train the model, it knows certain things and it can respond accordingly, right? You may even then go and fine tune the model after that for a specific business use case. But the world of information that is visible to that model is whatever was in the training data set. And that's a finite amount of information locked at a specific moment in time, right? And what RAG does is it gives models visibility into additional data that they weren't trained on, that they can go consult to get you a better answer, right? So you can think of like setting up an internal, kind of chatbot in your enterprise, in your company, if you want your employees to be able to do that. You could just grab ChatGPT and it would have great basic functionality just by using that foundation model. But it's going to be a lot more useful if you can connect that to your corporate SharePoint, right? To your employees' contents of their email inboxes or whatever. They're going to be able to give you much better answers. And that's RAG in a nutshell. And that's a whole heap of additional data that you need to now stick somewhere, and you need to be able to read it quickly in the course of information. So you have a bunch of storage needed up front. Whoever, OpenAI is training ChatGPT in their data center. Okay, they need petabytes of data to do that. But now, Solidigm or Weka or Geico or Jersey Mike Subs, whoever, some enterprise sets up their own RAG-enabled inferencing. They're going to need to consult additional data sets that need to be stored somewhere and that need to be read from quickly in order to give those meaningful responses that have kind of the more specific or more recent data incorporated into the understanding of the question and the answer that it delivers. So those are a couple of places on the storage side that we spend a lot of time thinking about, okay, how do we accelerate that, or how do we enable that to happen more efficiently, or deliver higher quality outputs of the model by letting enterprises store bigger RAG data sets with higher dimensionality. All that stuff can impact kind of the bottom line usefulness of the inferencing that's done within the context of, for example, an enterprise.
Now, Shimon, you've and the team at Weka have delivered a fantastic platform to address some of the things that Ace is talking about, a high performance distributed storage solution. Can you talk about why this is important and how you've addressed things like reducing latency and improving throughput?
Yeah, definitely. So I think, if we want to look at one of the key differentiators of the Weka environment is that we address performance in all four aspects of performance: throughput, latency, IOPS, and metadata performance for the data that we serve. And that's very unique because usually you need to pick from other environments, you need to pick one or the other. But with these AI use cases, we see that they're all of the data is being accessed, obviously, by different parts of the pipeline in different I/O patterns. So the ability to provide high throughput at a very low latency with high IOPS at a very high metadata is providing a differentiator factor. Talking about the topics that Ace mentioned, and I'll also say that we're seeing them in many cases because inferencing is still being explored. Customers don't necessarily associate these challenges as challenges for inferencing, and it's on us to educate them a bit from what we're seeing at other large-scale customers. I would say that where distributed storage comes into play is when you look at a GPU environment, at an inferencing environment, Gen AI inferencing environment at scale, you never have one GPU server with local capacity. It's always a distributed environment. We see customers running hundreds and thousands of inference servers just to accommodate for customers low latency of prompt reply for the inference request. I'll touch these topics specifically. For example, for RAG inferencing, as Ace mentioned, you need to feed this RAG environment with a lot of data so that the model can now query them. And this query is actually being done in real time. So when a prompt go into my inference environment, I need to now run my query on the vector database that holds these embeddings, that holds that data, and enrich the prompt as it goes to my model and provide a reply. Obviously, the faster that my vector database can search the tables that will reside. Essentially, eventually they will overflow to the shared storage. The faster that they can reply, then the faster the LLM can reply to the prompt. And obviously, in prompt inferencing, latency is king. That's one thing. There's also the previous task of the vector database embedding. So once I have data, how fast can I read that data, the distributed data of my organization, and push it into the vector database? So the embedding part of the vector database and the querying part of the database are served well by a Weka environment with low latency. And then actually the thing that we're latest excited about is the distributed KV cache that Ace mentioned. Eventually, if you have thousands of servers, even if they have enough GPU memory between them, the prompts are being sent to different GPU servers. So eventually, I need to share the context between these different GPU servers, and they can recompute the context constantly, and that's what we're seeing in many cases. But once they're using a Weka environment, they can, instead of recompute the context, they can just load the key value that another GPU server saved on Weka. And I'll just throw a number. We just actually released an interesting blog about it with an experiment we did. GPU server that was pre-filling 100,000 tokens took around 24 seconds to pre-fill these tokens. That was a Llama 3.1 model, 24 seconds. When another GPU server loaded that same amount of KV cache from a Weka environment, it took half a second using our GPU direct storage technology. So 24 seconds were converted into half a second. Imagine how many more tokens per second can be generated if you're now shrinking the context, the time to generate or to answer these questions. So these are only two. By the way, there's auxiliary advantages as well that are almost obvious. In no environment are you using only one model. So even when I have a distributed inference environment and I'm throwing prompts into it, I have multiple models loaded and unloaded in order to answer these prompts. Loading and unloading models is also a task that can take anywhere between a few seconds to a few minutes, depending on the architecture. Shrinking that is valuable because then you can accommodate for more users. There's more values like mixing inferencing and training clusters, but I imagine we'll talk about it more in the future.
You know, it's interesting when you're talking, Shimon, we've had Weka on the show before, and you've talked about your distributed system, and it's always been in the lens of training, you know, earlier conversations for earlier times, I guess. But one of the interesting things to note is that inferencing also relies on remote storage. And I think that this is significant. How does it affect system design as you're looking at working with enterprises and deploying distributed storage for their inferencing workloads?
So what we're seeing, one of the interesting aspects is that we're now seeing these training clusters that are converging with inferencing clusters. So a customer that would typically do one thing now does both, and utilizing a distributed storage for the same reasons that I mentioned before for inferencing, actually now allows them to converge between the two clusters and saying, we understand how training works on Weka, we understand how inferencing works on Weka. Now, what if we could utilize Weka to enable both? And I'll give you an example. We have a customer that's running at scale, hundreds of GPU servers, and inferencing is their main goal. Inferencing is eventually how they sell their tokens eventually, right? So what they do periodically is, as their inferencing requests increases, they actually use our fast checkpointing capability to checkpoint their model training on some of their training servers, and then increase the inferencing servers onto these GPU servers, utilizing that fast model load capabilities that I mentioned. So they know that in a predictable way, they can now switch between inferencing and training constantly. By the way, we have customers that are more on the scientific side, and they're actually prioritizing training on inferencing when they can. So being able to also overflow into the inferencing side periodically is interesting.
Now, I think that one of the biggest challenges is balanced infrastructure delivery. And I think that one of the questions that I have is how do organizations ensure seamless integration between their GPU compute and storage systems to maintain a high performance environment?
I'll take
Yeah,
that.
this is probably something that the folks kind of building and managing the hardware clusters themselves are most worried about, right?
Mm-hmm.
If you're a company deploying an AI solution to solve a problem, you may not think about it at this level of detail, but it turns out that making smart choices about where and how to pair storage solutions with GPUs can have a significant impact on your outcomes, not just in terms of quality, but also, cost efficiency, power efficiency. Um, and so, what I'll say in like broad strokes that we've seen, you typically have your local storage that's direct attached to GPUs in a compute server. That tends to be relatively limited in terms of the amount of storage you can fit in those boxes. If you look at something like the latest NVIDIA DGX boxes, they have like 8 slots for local storage, and you can put SSDs in there. And then for everything else that doesn't fit in there, you're going to be connecting over the network to that remote storage. And that may be storage servers that have 24, 32, storage slots a piece in them. And it's important to understand that hierarchy because you want to accomplish very different things with storage in those two different locations, right? So if you look at the inside the GPU servers, the name of the game is really GPU utilization. Folks have laid out a bunch of cash on these highfalutin new GPUs, and they want to make great use of them, right? If they're running them at 50% utilization, they're losing out on a lot of ROI there. And so that's where you tend to want to put really fast storage devices. Gen 5, PCIe Gen 5 devices, typically built with TLC NAND as the media inside, give you the option to run really fast and feed those GPUs so they're not starved for data in the course of doing their work. So for Solidigm, that's something like our D7 PS1010 product. You don't necessarily want to fill your network attached storage boxes with that same product, right? In part because your performance constraint is really going to be network bandwidth. You can't use all that great Gen 5 SSD performance across the network because it'll bottleneck on its way to the compute servers anyway. So the focus there becomes about scale and efficiency, particularly if you have these use cases where you're dealing with terabytes or petabytes of data. Doing that in a manner that is both power efficient, space efficient, and cost efficient as well is kind of the priority on that side of the hierarchy. And so that's where a product like the D5 P5336 from Solidigm is a recommended one from us for that part of the cluster. It's a Gen 4 product, so the performance profile is more read optimized. It's not necessarily optimized for really fast writes in the way that the PS1010 is. But that's because it's you need a broad portfolio of products to sort of fit the different needs and how they go into something as complicated as an AI cluster. And so we generally say, go fast and your key metric is something like GPU utilization or time to result, when you're training a model in the compute servers. And then on the storage server side, because they're network connected, that's where we're talking about, gigabytes per dollar or gigabytes per watt tend to be the metrics that we encourage folks building out these clusters to think about that'll kind of lend themselves to better, more optimized outcomes at the end.
Now, this has sounded fantastic, and I can see the opportunity for enterprises. But do you guys have any examples of enterprises that have actually managed inferencing models at large scale? And what lessons can be learned by others from these early examples?
Yeah, maybe I can start.
Mhm.
We have multiple organizations actually doing this large scale inferencing environments, and we see some of them are internal usage only, and some of them are providing that as a service. We see some of those running on on-prem environments, and obviously, when you're running on on-prem, it's considered to be the highest performance because of the network environment, no virtualization. But we're actually seeing that a lot of the new inferencing environments are also beginning on the cloud. So we have customers running inferencing on, for example, AWS connected to Weka, or also on GCP and Oracle clouds connected to Weka. We're starting to see some on Azure as well. The value of running on the cloud for inferencing that these customers are benefiting is actually the ability to auto scale. So it's interesting to start with a certain GPU footprint, GPU servers footprint, and accommodate for a certain prompt latency. Maybe it's 0.8 seconds or something like that. And then as the load increases on these GPU servers, the design of these smart inference environments is actually to scale out as you need to. So to scale out with the amount of GPU servers, as I mentioned, could be that you had additional GPU servers that were doing training. So you stop the training and increase the inferencing on top of them, or could be that you're allocating from a pre-allocated, non-used buffer of GPU servers. But just the ability to expand your inference cluster in a fast fashion allows you to accommodate for more prompts peaks, which occurs, right? And then scale down as needed, so you don't need to pay for that inferencing environment. And then the challenge is, how do you do it in a make sense way? Does it take you 10 minutes to? Well, one of our customers took 10 minutes to expand into new GPU servers. When they moved to Weka, it became around half a minute to scale up to a new GPU, because then eventually scaling out to a new GPU environment means that you need to instantiate it, you need to load the OS, you need to load the models and the weights into GPU memory and activate them and be able to accept these new prompts. So that's definitely one learning. Another learning is, how do you create a multi-cloud environment for that inferencing? For example, you're training your models in one environment, and now you're serving them in another environment. Could be a different cloud, could be a different AZ, different data center. How do you create that synchronization? Because you always want to make sure that you have your source of truth, and then be able to expand to where you get the GPUs. Sometimes you're getting them on a single environment. Sometimes you're getting 1,000 GPUs on one cloud or another. So for that, for example, we have customers using our data mobility capability to different locations. So train on one cloud, send the data to another cloud, just to make sure that the data is resilient and the data is available for the GPUs to load the models from. Another thing is, we're now seeing honestly, that most customers, they're very advanced customers that they know what they're doing, they're running inference, they explored. And now we're seeing a lot of the enterprises customers that are, my CIO told me that I need to have a Gen AI strategy. I bought some GPUs. I know what I want to do. How do I get there? So honestly, a lot of the learning is, we released something that it's called Warp, Weka AI RAG reference platform. It's a blueprint where we took some of the accumulated knowledge from some of the large customers, and we put it into a blueprint saying, hey, Mr. Customer, if this is your day 0, day 1, day 2 of creating your inferencing environment, these are the components, these are the accumulated learnings. These are the components that you need for an AI inferencing environment at scale. So everybody can open a Jupyter notebook and connect to a vector database, run a model, run Olama even on my laptop, right? But if I need a scalable enterprise architecture, which components does it need? So for that, we created this blueprint. Customers can just utilize it, look at it. We're now creating a deployment for it for their benefit.
That's amazing.
And if I could jump in quickly on
Sure.
top of Shimon's excellent
course.
comments. We see inferencing being used to solve problems on scales large and small across industries, right? It's really a watershed moment for technology and probably for the human race, at the risk of waxing a little too poetic here. But as you look across some of the really cool problems that this stuff is solving, you know, code development, medical research. I mean, we could list stuff all day long. My view is that, you know, if we're successful here, it's not because we're injecting the infrastructure conversation in the middle of all this. It's really because we've gotten that out of the way, right? And we've freed up the thinkers and the problem solvers, the data scientists to go do great work that's going to benefit all of us, right? And so going back to a comment Shimon made at the very beginning of the conversation, which I really liked, I think we have a shot here at entering an era where the real limit on this stuff is the human imagination, right? That's a big lesson. Talking about what we've learned from the examples we've seen so far is that we're closer than ever to having, you know, a realistic claim that that's the main impediment to our progress in solving some of these really intractable problems that we've looked at as a society for years and years. And yes, the stuff under the hood enables that to happen, and we're very proud of the contributions that we and our partners are making to make that more possible. But at the end of the day, like, you know, the notion that our constraint going forward ought to be only just, you know, our imagination to solve some of these problems is something that I think is, you know, kind of moving from the realm of fantasy to an actual lesson learned as we see more and more examples of that happening, and more instances where the thinkers and the technology providers are working together to you know, sort of unlock possibilities that were just, you know, unthinkable even a decade ago.
Now, that was beautiful. And I think that one of the things that I'm excited to see is how all of these core capabilities across use cases expand as enterprises start taking advantage of this technology. Obviously, as they continue to innovate, it will require that you will need to continue to innovate as well. I think the last thing that I want to touch on from you is, what infrastructure innovations do you foresee becoming critical for future scalability and for future requirements from enterprises? What are you working on today that might impact the solutions that are deployed tomorrow?
Yeah, it's a great question. I can't open up our whole product roadmap and talk about all the neat things going on in the lab, but certainly a trend that I'll point to that's only going to accelerate the work that's being done is this notion of hardware, software, co-design, that it's no longer enough for folks in a silo to make great software and then go shopping for hardware. It's no longer enough for hardware companies to make great components and then, you know, try to plug them into existing software solutions. It's something that you're hearing more and more about in the news, and I expect that only to become a bigger deal as time goes on. The idea that these technology providers need to work together at a very early stage with specific kind of solutions and outcomes in mind, and co-develop these things together. There's a level of integration that AI demands that's probably greater than anything we've ever seen before. And so there's an opportunity and there's a challenge before, you know, both the kind of hardware and software industries to figure out how to do that in an effective and an efficient way, because that's going to you know, deliver on promises that we just can't if we're working separately, as smart as the folks in each silo might be, right? It's got to be a joint effort, and there's got to be sort of new working models, new paradigms between you know, historically kind of separate solution providers in this space to really get us as far and as fast as we can go.
Maybe I'll add to that.
Mhm.
Some of the obvious challenges that in the immediate future that we all see is power. How do we become more power efficient, right? We were talking about data centers that are, and even racks that are requiring massive amounts of power, generating massive amount of heat to cool. That's a big challenge. It's not a storage challenge. It's a big challenge. How do you do it in a sustainable way? There are ways, if you're looking at what we're doing at Weka, into reducing the power footprint, for example, by folding all of the Weka environment into the GPU servers themselves, eliminating the need for external storage as well. We were actually seeing a lot of data centers adopting that, whether it's on-prem. We actually see customers on the cloud doing that as well. Additionally, if we're looking at, as I mentioned, it's not, if you're now providing a solution for AI environments, you're not providing a component in the ecosystem. You can, but that's not the road for success for you or your customers. The road for success is the collaboration between the multiple layers. If we're looking at, again, if I'm looking at that Warp environment that we released, it's composed out of multiple layers that all provide the functionality. The users cares about this, but there's like 10 other things, 20 other things underneath. How do you create that connectivity, that synergy, where all these components are not just built on top of each other, but they're working together? So there's a way, for example, we're seeing customers constantly copying data between different environments, local NVMEs, object stores. One way to use Weka is, for example, just forget about it, just use it, right? But more than that, how do you make sure that frameworks are benefiting from your environment to the maximum, so they can provide the maximum capability to the upper layer, right? So one of the things, so we are describing some of these things in that Warp architecture, but more than that, if we're looking forward, at least in Weka, what we're looking at is, if you look at the Weka low latency environment, almost as an extension to the GPU HBMs, to the GPU memory. We all know that there's GPU memories is in the nanoseconds. Weka is in the microseconds. Usually storage environments are in the milliseconds. But if you had that microsecond to nanosecond interlock, what can you do more that would actually even accelerate these outcomes even further? So the 24 seconds to half a second is an example. There's more things that we can do around model loading, unloading, on the storage layer that these environments would benefit from. So stay tuned for that. That's the direction that we're now looking at. And that's a completely, eventually, is what value can we bring to these environments if we interlock in that fashion with them.
So Shimon and Ace, this has been an awesome conversation. I have one final question for you. What advice would you give enterprises that are listening today on looking to future-proof their AI infrastructure in the face of rapid technology advancements, and how should they work with you?
I have one advice, and that's something that I'm seeing today that's being done. And whenever I talk with organizations, I urge them to take it. We're seeing organizations that are now looking at an environment, and they're sizing an environment for one use case, for today's use case. For example, here's an inferencing environment. Here's a training environment. Here's a pre-processing environment. And then when they put it into production, reality is everything runs on it. I call it mayhem. Eventually, there's a mayhem environment on it, because eventually you're running, even if you size it for training, somebody will say, hey, I need that data for inferencing. So, okay, I'll inference with it. Oh, but I need it for some embedding for my RAG environment. Or here's a cool AI application compiler that I'm running on it, right? So eventually, in order to future-proof your environment, you need to understand that it's going to be a mayhem environment. Everything will run on it. Make sure that when you're sizing an environment, don't try to size it to one use case. At the very least, size it to multiple use cases. We all know that these environments, as I really liked your comment, I'm going to use it, by the way, all the time, Ace. Last week was the longest year in AI. It's like if you're watching the news bulletins, every day changes. So the basic thing you can do is make sure that you understand that you're, at least if you're looking at the data environment, and definitely if you're looking at the upper layers, don't size for one use cases for today. Size for multiple use cases, because that will somewhat future-proof you.
Ace, do you have anything you'd like to add?
Very well said. I guess in terms of looking ahead and future-proofing, I'd circle back around to one of Shimon's earlier comments about power consumption. I think that's going to be an increasingly huge deal going forward. Right now, we get headlines in the news about it. Oh, AI data centers are, consuming as much power as X country or, whatever. There's a lot of different analogies out there being used. But we are starting to see, I mean, we've heard from some of our tech luminaries, folks like Sam Altman and Mark Zuckerberg have been on record saying they're already hitting a power ceiling where they can't build out their AI clusters as much as they'd like because of available power. We've seen if you were, it feels like ancient history now, but if you rewind to whatever, 2010, 2015, all the world's leading tech companies were making these zero emissions pledges, by 2030 or 2040 we'll be carbon neutral. And what we've seen in the last 3 years is all those companies quietly walk back from those because there's just so much value in AI that they're willing to make that trade-off, right? And hey, yes, it's going to consume a lot more power, and we haven't figured that out yet, but um, kind of the value that AI offers is too much to pass up, and that's fair. I don't fault anyone for thinking that way, but I do think as we look ahead, future proofing is a big part of it is going to have to do with power efficiency. And
Mhm.
I mean, the folks, building the frameworks and the algorithms to build models have to think about that. The folks training the models in big data centers have to think about that. The folks taking a model and running inference on it thousands or millions of times, have to think about that. But, I expect and I encourage folks to keep that kind of top of mind in
Mhm.
terms of future proofing is, obviously at Solidime, we're worried about infrastructure. And so make smart choices there. We happen to feel like we have a pretty good story there with our high density, QLC products, and we have some cool modeling you can check out on our website about, power savings on some of our really big drives compared to some of the other options out there. But the pace of advancement in terms of AI solutions has been pretty torrid over the last few years. And one of the great constraints on that pace going forward is going to be available power on the planet, right? And so that's going to be something that we're all going to have to think about and make sure we're optimizing for to be able to kind of maintain or even increase the pace of innovation that we've seen in the last few years.
Well, Shimon and Ace, thank you so much for being with us today. That wraps another edition of the Tech Arena Data Insights webinar series. And if you'd like to find out more about Weka and Solidime, please visit their websites. If you'd like to keep following content on Tech Arena, please subscribe, and we will continue to deliver fantastic editorial like what we featured today. Thanks so much.
Right on. Thanks a lot, Allison.